Exponential growth and decay, things that grow and die, not necessarily die because things that die exponentially never actually die. They never actually go away, but they do decrease or depreciate over time. Okay? Things that grow exponentially grow really, really fast. Things that die exponentially die really, really fast, right? They don't fully die, but they go down very, 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 very quickly. Okay? So that's what we're going to talk about today. So we're not talking about linear, we're talking about exponential. Okay? So a lot of these you're going to be like, oh, this is easy. You just, do. No, that's you thinking linearly. So we're talking about exponentially. So how do we solve this? Well, we're talking about rates of change. Rates of change we've talked about. Rate of change is the same thing as slope. Slopes are just derivatives. So that's where this part comes from. Is means equal, right? Directly proportional. You're going to see those words a lot. The word proportional, directly proportional or proportional, you're going to see that a lot. That's where this K value comes from. K is a number. It's not a variable. Okay? To Y. So this is what we're going to see a lot. Okay? dy over dx equals K times Y. Okay, so where do those letters come from? Well, K is the constant of proportionality. It's the part where it says when you see the problem, you're going to have a lot of directly proportional to Y. Okay, so the rate of change of a quantity is directly proportional to the quantity itself. So we state it as that, where K is either a growth or decay constant. So growth or decay is based on K, is what K is. Okay. Okay, so before we do any problems, let's do something we've done before. Solve by separating. Solve by separating. We have a dy and a dx. So how do we separate? When we separate, where do the variables go? So let me rewrite this. Where do the y's go? To the left, right? Where do the x's go? To the right. Just like we've done since last week. So dx's cancel out, y's cancel out. I get 1 over y equals dy equals k. K is going to stay on this side. Dx. Remember, k is a number. It's the constant. So I don't treat it like an x or a y. So the x's are to the left, or to the right. The y's are to the left. What do I do? What did I do after that? That was step 1 you guys did. What was step 2? Antiderivatives, right? We do antiderivatives of each side. Each side of the equals. We've seen this quite a bit, and we're going to see it quite a bit more. What is the derivative of 1 over y or 1 over x? Natural log of that letter, right? So natural log of y. Remember, if y is positive, whatever number we're plugging in, if it's positive, you don't need the bars. If it's negative, you need the bars. So that's why because it's always got to be positive. Equals. So what's the antiderivative of the other side? Kx, right? Because k is not a letter, we treat it like a number. So it would be kx plus c. Right? Okay, we did that. The next step was plug in numbers for x and y. Well, we don't have any numbers to plug in, so we can't do that. So what was the last step that we were doing? What was the last step? Solve for y, right? Solve for y. So I have to solve for this guy right here. So how do I get rid of the natural log? If I could get rid of the natural log, I'd be happy. What was the trick? It was the loop trick, right? To get rid of the log, we used the little loop trick. The loop trick said, well, all natural logs have a base of e. So the loop trick said we can go e to this power equals y. Change it. How do I get rid of a log? You change it to an exponent. How do I get rid of an exponent? You change it to a log. Okay. Okay. So that's what we're going to do quite a bit today. The nice part is we've done it before. Every step we just did, you've done quite a bit already. This just chapter. Okay. All right. So let's look at the first problem. Let's look at number 2. These are all context problems, meaning there's a story behind it. Bacteria, population, things growing and dying. Okay. Okay. So this case is bacteria. Bacteria are growing or increasing from 400 to 1600 in 3 hours. So in 3 hours, it went from 400 to 1,600 in 3 hours. Assuming that the rate of increase of the population is directly proportional. Here is our key that this is exponential growth and decay. Those 2 words right there. You see that? It's going to be exponential growth and decay. All right. Okay. So they want us to find an appropriate equation. Well, I'll tell you right now, since it said directly proportional, we're going to use this guy right here. The only difference is we have a context problem, right? I want to put my letters in context. In other words, I don't want to use X and Y. I want to use letters that work for this problem, right? So what are the 2 variables that we have that we're talking about? What are the 2 things that are directly proportional to each other? Bacteria is one of them. And time, right? Time and bacteria, right? They're directly proportional to each other. Time, I don't know how I think hours they're measuring time. Bacteria, I don't know how they're measuring bacteria, but it's a number, right? So time is always going to be X. Why is time always independent? Because I can't control time. Time just goes, right? I can't control time. So time is going to be my independent variable. Bacteria is going to be my dependent, or Y. Okay, so this is how it's going to look. D blank over D blank equals K times blank. Time is going to be my independent. Independent is what? X or Y? X. So that goes there, right? That's where dx usually goes. And then we said bacteria, however they're measuring that, is the dependent. Well, I'm going to use a capital B for bacteria. So it's the same equation we started with. The only difference is it's just in context. B means bacteria. T means time. First thing we got to do is solve this guy. How do we solve it? Solve by separation. Usually y's went to the left, x's went to the right. We don't have x and y's this time. So what's going to go to the left and what's going to go to the right? B's are going to go to the left. T is going to go to the right. Good. So I have 1 over capital B dB equals K dt. Okay. Next step, antiderivatives. I told you guys you'd be seeing this quite a bit, and we're already seeing it. What is the antiderivative of 1 over b, 1 over x, 1 over u, 1 over y, 1 over anything? Natural log of b. The other side is going to be k what? T, good. Plus c. Good. We're not solving for b this time, or sorry, we're not solving for y, we're solving for b this time, right? That's the letter we're choosing. So b is going to equal what? There you go. E to the k t plus c. That's the generic or the general solution, right? This is the general solution or the generic solution, however they call it, however they talk about it. So now I have to use my numbers. So what I'm going to do now is I have some values. They've told me about it, right? So I'm going to make a little table over here. Over here in the corner, I'm going to make a little table. The independent was time, t, right? The dependent was b. So time is in hours, bacteria is in whatever, however they're counting bacteria. So we know we have 400, right? It said we have 400 bacteria at one time. What time was there 400 bacteria? It's 0, right? Initial. So we're going to put 0. At 0, there was 400 bacteria. And then there was 1,600 at 3 hours, right? At 3 hours. Okay, so what I have to do now is 2 things. First thing is I have to solve for C. That's the first thing. And then I have to solve for K. That's the second thing. Okay, how am I going to do that? I have 2 points, don't I? 0, 400, 3, 1,600. So the first thing I'm going to do is solve for C. So everywhere I see a T, I'm going to put in a 0. Everywhere I see a capital B, I'm going to put a 400. That's the first thing I'm going to do. Okay, so 400 equals e to the c, right? How does that help us? Well, it helps us like this, right? Watch. I did this the other day. I don't know if you remember it, but I did this. I can separate these 2 guys here. Using that, right? That's using the exponent rules, right? Anytime you add exponents is when you're multiplying with the same base, right? So what I just found was this part here. So what I'm going to do is I'm going to plug that in now. I'm going to plug it into my new equation. So B equals 400 times e to the kt. Put a little note. E to the c is always going to be your initial amount at t equals 0 or whatever equals 0. So whatever your initial amount was, that's what that's going to be for future reference. Okay. One more thing. I got to find K now. Well, I already used 0, 400. I can't use it again. But I can use 3, 1600. So I'm going to use 3, 1600 to find what K is. Okay. So 1600 equals 400 times E to the 3K. I got to solve for K. First thing I'm going to do, divide by 400. E to the 3K equals 4. 400 goes into 1600 4 times. The letter I want to solve for is up in the sky. How do I bring it back down to Earth? Not a log, yeah. That's the question logs answer. Logs or LNs, when do we use them? It's when we're trying to solve for a power, right? Anytime we're trying to solve for a power, right? We use natural logs. Natural logs, the most common thing you see in natural logs are like earthquakes. You heard about the Richter scale. It was a 3.0 earthquake, 5.6 earthquake. That number, 5.6, 3.0, that's an exponent. That's the magnitude. It's an exponent. So how do they solve for that? They use a log because those are exponents. So when they say it's a 3.5 earthquake, that was the magnitude. That was the exponent. How did they solve for it? They used a log. Okay. So how do we change? So we have E equals E to the 3K, equals 4. How do I change that to a log? Exactly. There's another trick, kind of like the loop trick. It's called the L or the boot trick. You do this, make kind of a boot, right? So you take the log. The first thing I hit was this guy, right? When I did the boot, first thing I hit. So you take a log of this, which is a natural log, right? And then the next thing I hit was 4, right? That goes in parentheses. And then the last thing I hit was 3K. It's a little trick. It's not the only way, but it's kind of like the little loop trick. Loop trick works when you want to go from an exponent to a log. This little L or boot trick goes when you want to go opposite direction. Okay. Divide by 3. So I got K equals 1/3 natural log of 4. Last step, plug that in now. B equals 400 times E. K is now 1/3 times the natural log of 4 times T. That's my particular solution. K is solved for. C is solved for. That's the one that we want to use, that we're going to use to solve these Lex questions. Here's the nice thing. We just did pretty much the hard work. After this is our formula we're going to use for these problems. So when they ask us questions, we're just going to plug numbers in, get an answer. That's what we're going to use our calculator for. Okay, so here we go. Find the number of bacteria at the end of 6 hours. So in other words, they want to know, what is that number going to be? This is what happens a lot of times. I see this a lot. Oh, well, in 3 hours, I went up 12, right? So aren't another 3 hours, I'm going to go up another 1,200? So shouldn't that be 2,800? You're right if they grew linearly. That's linearly. Exponentially is a different animal. Okay? So patterns are good, but if you get the wrong pattern, you're not going to get it right. Okay? So it's not linearly. Linearly was how you looked at things in Math 1. And we still look at linear lines, but this is exponentially. Okay, so 6 hours, right? So what we're going to do is we're going to use our solution we came up with, b equals 400 e to the 1/3 times natural log of 4 times t, right? And we're going to plug in 6 for t. Calculator. So, again, the thing I like about NumWorks calculator is literally your answer. When you plug in things, it's going to look exactly like that. So we're going to go to the calculator. So again, if you're home, you'll always start at home, hit the calculation part. Now it's a calculator. So we had 400, right? Times E. E is right above sine, which is 2 above 7. Now, parentheses, 1/3 I use parentheses more because that's just the way it works. Natural log 4 parentheses, parentheses. And then the number I'm plugging in is 6, right? I should use parentheses for 6 too. Okay, E, the E button is 2 above 7. The natural log button's right to the right of that. Okay, hit enter. 6,400. Okay. All right. Done. That question was super easy once we had the formula. The formula is going to be, I don't want to say the tough part, but that's going to be where the most of the heavy lifting is done. Okay. All right. Sometimes for these types of questions, sometimes for this question, you'll get a decimal. That's okay, just round the decimal to I would go 3 spaces. We're going to see some decimals later. Okay, next question. Radium-226 is an element. It loses its mass at a rate that is directly proportional. That tells me we're going to use what we've been doing to its mass. Okay. If its half-life is 1,590 years. Okay, so science time. What does a half-life mean? It's kind of self-explanatory, but what is when I say a half-life? What does that mean? It's decreasing. So if it has a half-life of 1,590, what's special about 1,590 years? It's going to have half its life left. Yeah. So every 1,590 years, it's going to maintain half of what it had before. So if it had 100, In 1,590 years, it's going to have 50 milligrams left, right? So by that logic, is it ever going to go away, become zero? No. No, right? That's half-lives. See, someone like, I always do this to my math 3 class when we talk about exponents, and they don't believe me. You have a pizza. Take half of it. Come back and take another half of it. Come back and take another half of it. Come back and take another half of it. Will there ever be no pizza left? Theoretically, no. Theoretically, but the slice will be so thin that there really isn't any. But theoretically, if you always do that, there will always be pizza there. When I say that to my math 1 or my math 3 classes, they don't believe me. The pizza's going to be gone. No, theoretically, if you keep taking half of something, there's always going to be something there. Might not be much, but there's always going to be something there. Okay? So that's what half-life is. That's what half-life is. Okay? Okay, so, and if we start with a sample of radium-226 that has a mass of 100 milligrams, find the formula. Okay, so now they want us to do what we did in part A of the last thing. Give me this guy here. Where do we start? We start up here. Start with letters. Start with letters. What letters am I going to use? I don't want to use X and Y because it's in context. Anytime you're doing something in context where there's a story behind it, you want to use letters that are appropriate. You want to use symbols that are appropriate. So, what are the two variables? So, radium, right? Mass, how much of it is left? So, you can use R or M. Either one's okay. And then what's the other? T, for years, right? T, time. Okay, so time is always going to be X. Time is always going to be independent. And if you want to use R, capital R for radium, that's great. If you want to use lowercase m for mass, that's okay too. Whatever you want, that's okay. As long as you do that. Have that going. Okay. R's to the left, T's to the right. Check. Antiderivative. This whole process is feeling very, very familiar. Just different letters, right? Let me finish this problem and then I'll tell you. So we have natural log of R equals KT plus C. When you keep doing the same thing over and over again, it's okay to start skipping steps. I don't mind you skipping steps. What is this going to equal? It's going to equal R equals what? E. There you go. So if you can do this, if you can go from here to here, I don't need to see this work anymore because I know we've been doing it, right? If you need to do this to get to here, keep doing it. But if you don't need to keep doing this stuff here to get to here, don't do it. It's up to you. Okay? Okay, so, and then like we did last time, R equals E to the C times E to the KT. So our first thing is we got to solve for e to the c. The second thing is we got to solve for k. So let's go make our table now. We have time and we have bacteria. Oh, not bacteria, radium. What do we know about how much radium is left after a certain time? It's half, right? So do we know how much we start with? So at time 0, we start with 100. And then we're eventually going to have half, right? When are we going to have half? Right? And then when am I going to have half of that? So 1,590 times 2, let's see here. 1,590 times 2, 3,180 years. I could keep going, but I'll stop there. You get the idea. And then in another 1,590 years, I'd have 12.5 left, right? What did I say about this guy here? I said it earlier. E to the C is always going to be your what? Initial amount starting value. So what is our starting value? 100, right? So guess what? You can solve for it the way we did on the last problem, but why keep reinventing the wheel? It's just going to be our starting amount. Step 2, solve for K. So I'm going to use one of my points. I can't use the first one because I technically already did to get 100. So I'm going to use my second point. Okay, so anywhere there's an R, I'm going to put a 50. Anywhere there's a T, I'm going to put 1,590. Get T by itself, divide by 100. Yes. Oh, okay. So K. Okay. So we got 100 equals E to the 1,590 K. How do we get K to the ground? Natural log, right? So natural log of 1/2 equals 1,590 K. Divide by 1,590. So I get K equals 1 over 1,590 times the natural log of 1/2. Okay, so plug it back in for K. I have R equals 100 E to the 1 over 1,590 times the natural log of 1/2 times T power. That's the formula I'm going to use. Last thing I want you to do is use it to find out after 1,000 years how much of it's going to be left. After 1,000 years, how much of it's going to be left? Parentheses 1 divided by 1590. Natural log 1/2 times, what was it, 1,000? The heck? I put something wrong? Are you guys able to see what it is? The decimal part? Yeah, scroll down. Oh, there we go. There we go. Yeah, thank you. So we got a decimal. It's okay. Round, I usually go unless they tell you how many places, go 3 places. So 64.666. It's going to be milligrams. Very last question. Does that number make sense given our table? Does it fit with what our table is? It does, right? From 0 to 1,590, we go from 100 to 50, right? 1,000 would be right in the middle there. That makes sense. Okay. And then tomorrow we'll finish this up. Okay.